Okay, so here we go. Well, before I get into the math, let me just say great job on the exam. This is the highest class average on an exam that I've had in years. So I'm very happy about that. And of course, letter grades are correspondingly high, and everybody likes that. Okay, here's what we were doing last time. We were talking about iterated integrals. And recall, an iterated integral is an integral of an integral, which is a little weird when you think about it. But on the one hand, so we're doing an integral in this direction, cross-sectional area times dy to give us volume. But then we realize that in order to compute that cross-sectional area is itself an integral. So thus, an integral of an integral. Okay, and this is great for computing volume under a surface, such as we did in this example here, which is nice. But we ran into a dead end when we started to try to apply that to other things that we might, one would expect that we might need to compute integrals of. So, for example, you try to compute mass by way of this argument, and you find yourself writing down, here inside of the inside-most integral, where in some sense it all begins, and you're multiplying mass per unit area times length, which isn't a thing, right? That's, I don't know, we could force our way down that road and try to make sense out of it, and you can, but it's a tough road, and wouldn't it be nice if we didn't have to do that? So that's what we're going to pick up now, and we're going to talk about a new idea called a double integral. I'm going to have to segue into it a little bit. First, I want to remind y'all that let's say this. Don't forget single variable calculus is prerequisite, right? So I'm going to assume that y'all are good on single variable integrals, and in particular, the definition of a single variable integral is as a Riemann sum. So I hope that y'all are comfortable with that. If you're a little uncomfortable, perhaps, if, as in many single variable calculus courses, if your experience maybe kind of swept that under the rug a little bit, I've got a recording on the miscellaneous topics playlist of my YouTube channel where I discuss it. It's still kind of a summary, of course, but much more at length than I'm going to talk about here today. So please make sure one way or the other that you're rock solid comfortable with the idea of a Riemann sum. And I want to address a misunderstanding, what I consider to be a misunderstanding. A lot of people think that the definition of an integral is that it's the area under the graph. This is importantly wrong. It's really wrong. It's a problem, and let me try to explain why. Here is the reality of when we're using integrals to do stuff. And I'm not being ivory tower mathematician here. I'm talking about, practically speaking, rubber meets the road. Let's get stuff done and compute, stuff like this. I want to compute the mass of a thing, or the economic, the value of some sort of a stock derivative or whatever. Whatever the case may be, there's various different applications of integrals, of course. You cannot make a direct argument such as, well, I want to compute the mass of a one-dimensional rod, and of course, naturally, that's area. How does that work? In what sense is a one-dimensional mass just clearly and obviously equal to a two-dimensional area? That is a non sequitur. It doesn't make sense. Now, any case that one could make along those lines, the more reasonable this argument gets, the more it becomes kind of effectively indirectly a two-step argument of, we argue that mass can be computed with a Riemann sum, and that Riemann sum can be interpreted as an area under a curve. And sure, yeah, right, absolutely. But the point there is, the actual first step is to recognize mass as being a Riemann sum. Excuse me. Okay, so once you've made the connection that mass is a Riemann sum, you don't really need area. Why go to the trouble of reinterpreting that Riemann sum in terms of area under the curve when it's not necessary? Riemann sums, aka integrals, you can compute directly. Right? So it's very important that the idea of an integral is as a Riemann sum, because that concept, the concept of a Riemann sum, that is the thing that connects to all of these applications. This is not mathematicians being, proofy and formal. Riemann sums are the stepping stone, the necessary, the only way to get to all of this important stuff, practical computations. Step one, recognize it as a Riemann sum. And, while you're doing that, if you want to view area under a curve as being a nice little visual aid, well, I suppose. But it's certainly not part of the real, actual argument. Okay, that's all I'm going to say about that. And again, reminder: if you're a little shaky on Riemann sums, and as the definition of an integral, take a look at that video that I have up there. Okay, or any of a number of other options online, I'm sure. Okay, so we need to come up with kind of a two-dimensional version of a Riemann sum. Here we're going to be doing something that is importantly different from a single variable integral. By contrast, let me point back to here. Yeah. What we did last time, and for the first couple of minutes of today's lecture, was really kind of creative application of an old idea, single variable integrals, to a new context, namely, how do we, let's compute volume under the graph of a multivariable function, right? So we're kind of forcing single variable ideas into a multivariable context. And it has its uses, and that's nice, I suppose. But now we're going to develop a truly multivariable generalization of an integral. Single variable aside, right? We're not going to reproduce single variable integrals. So the idea of a single variable integral is if you have an interval, then you chop it up into little pieces. And then on each little piece, such as, let's say this piece here, on that little piece, you can write some stuff down. Maybe you want to multiply height times width to compute area, or maybe you want to multiply mass per unit length times width to get mass, or maybe, again, millions of applications. The point is, a construction like this to compute something, and then you add up over all the pieces. So I'm just going to take that concept and apply it to this dimensionally different scenario here, where now instead of an interval, let's suppose I have an entire rectangle. Maybe there's some mass involved here, and the mass is distributed over this rectangle, and I want to compute the total mass. Or maybe this is Colorado or Wyoming, and I want to compute the population, right? Something like that. So stuff distributed over area, not stuff distributed over length. So the big idea is it's exactly morally equivalent, which is I'm going to look at one piece at a time, right? Having chopped up the region perpendicular to the x-axis, and having also chopped up the region perpendicular to the y-axis. Having chopped it up into little bitty sub-rectangles, in other words. We're going to look at one little sub-rectangle at a time, and I'm going to argue, I think pretty believably, that on this little piece, if I want to know how much mass there is in that piece, well, mass per unit area times area. If I want to know how many people live in that little, county or what have you in Wyoming, then, population per unit area times area. Everything fits. It's all reasonable ideas, right? If I have population per unit area and I multiply by area, I get population. Nothing weird, no new questionable concepts, just plain old stuff. And then I add up over all the pieces. Now again, different, right? If I want to add up over all of those pieces, then it's not just, let's see here. I'm going to kind of, 1 to n. I mean, on the one hand, x, on the x-axis, my subscript's going to go from 1 to n. But also, furthermore, at the same time, in the y direction, my subscripts need to go 1 to n also, independently. Right? So I'm actually going to have a summation where both I and j both go from 1 to n. I therefore have n squared separate little pieces that I'm adding up. Not just n pieces like here. Here we have n squared separate pieces. And taking the problem, chopping it into little pieces, adding up the answers over all of those little pieces gives us the whole. And that's going to be our strategy. This is our analogous sort of two-dimensional analog of a single variable integral. What do you think? Big picture seem like a reasonable thing? Now, don't lose track of the fact that there are some annoying details to keep track of. And so when you're chopping up the interval from A to B, y'all remember these formulas, I'm sure, as to, what is delta x and what is x sub I and, all those details. It's the same exact stuff that we had here in single variable calculus. That's all the same. What's slightly new is that we are simultaneously doing the same thing in the y direction, not from A to B. X goes from A to B. In the y direction, we're going from C to D. So we do get different formulas here, but you notice they're morally very similar. Same idea, chopping it up into a bunch of little pieces, and the pieces are therefore this big, and you move over by that amount each time, j increases, etc. So details. But the big picture, the most important takeaway of a double integral, which is what we're about to define, is that we're taking the area of a little subrectangle. We're multiplying area times some integrand for some reason appropriate to your application. Again, if you're computing mass, then you want mass per unit area to multiply times area. If you're computing total population, you're going to multiply population per unit area times area, etc. And then having done that, again, you're adding up over all the pieces. And again, that's going to be there is the total. And so this is at least an algebraic way to write down a strategy for how to compute whatever it is that we're computing. Now, there will be the separate question coming up very soon, which is how do you actually compute that? Right? Is there a fundamental theorem of calculus for double integrals? Fingers crossed. Right? How do we actually compute these things? We'll get there. For the moment, I just want to focus on what the strategy is for taking an abstract question like how much mass is there on this sheet and turning it into an expression that I can kind of get my hands on. Okay. All right, so there's our definition. This structure here. This is called a double integral. We use this notation, which I think is pretty believable. Let's talk about the particulars there. dA is just representing that height times width gives us area. That's the size of that little piece of the rectangle. Whatever the function is that we have to evaluate to get mass per unit area or whatever it is our integrand for our application. Now that function goes in the middle, exactly as suggested by the Riemann sum. And then, just like in single variable calculus, we represent the summation with the integral symbol. Here I'm going to use two integral symbols. For reasons that'll become more clear in just a few minutes. But for the moment, let me just say we'll use two integral symbols because there's two indices here. Not only does I go from 1 to n along the horizontal, but j goes from 1 to n independently along the vertical. So So two separate kind of directions of the summation. Okay, so with this definition, and a quick aside, just a quick cultural point. Again, I'll remind you our textbook is a little bit higher cut than this course is, and which is nice in a lot of ways. But here the book spends some time kind of flirting with introductory real analysis, talking about some things that really would make more sense in Math 431 than Math 219. So I'm not going to do any of this stuff about irregular partitions and test points. It really does matter in some circumstances. These are really important ideas. It's not preposterous. This is good stuff. But we're going to be in this course focused on continuous integrands. And when your integrand is continuous, none of this stuff makes any difference, and so we're not going to bother with it. Okay, so you can skip all that stuff in the textbook. Okay, so let's do our first application. This is arguably a question we've already answered, but we're going to do it this time with double integrals. And so specifically, we're looking at a graph. Keep in mind what a graph is, right? Z equals. So we've got this surface here. And let's see here. The question is to compute the amount of volume under that graph. Fine. I'm going to compute that amount of volume. And here's how I'm going to apply our brand new concept of a double integral. I'm going to argue that this amount of volume is the sum of little pieces of volume that look like this, where I get one of those, I call them French fries, for each little piece of area down here in the domain. So the idea is I've taken my domain and I've sliced it in both directions. Oh gosh, this is harder than it looks. There we go. Sliced it in both directions, and for each little piece of area that I slice up the domain, there is a corresponding French fry. And the sum of the volumes of those French fries over all of these pieces in the domain is going to give you the total volume in question. Does everybody buy it? Okay, so the whole is the sum of the parts. Chop it up, add it up as one of my little pithy summaries for how to represent what's going on. We're taking a hard question, namely this whole volume, but by chopping it up into little pieces, I get individual pieces of volume that are easier to write down, and the whole is the sum of the parts. So we chop it up into little pieces, we add up those little pieces to get the whole. Okay, and having done that, easy to argue, if you just look at our little French fry here, that volume is height times the area of the base. I mean, geometry. I mean, there's a little round off error at the top where it's not exactly flat, blah, blah, blah. Goes away in the limit, not our problem. But roughly speaking, height times the area of the base. How are we doing? Everybody with me? Okay, so what we have done, without having to make any vague references to cross sections and integrals of integrals and sort of more blunt things like that. Volume is a Riemann sum. It's one of our brand new two-dimensional Riemann sums, which is a double integral. Now, I emphasize, it remains that we don't know how to compute these things, right? And that's going to be our big next question. But just in terms of turning a question into an algebraic object of study, that is pretty straightforward, right? The whole is the sum of the parts. You just have to chop up the whole domain. Okay. All right. So now, before we do another example, I want to capitalize on a sneaky, huge benefit that comes out of this example that we just did here. I'm going to quickly skip something I'm going to come back to momentarily. I want to talk about this diagram. So first of all, what we did last time, we computed volumes with iterated integrals, right? The slice of a slice and all that. And then iterated integrals, of course, are really literally single variable integrals. We know the fundamental theorem can compute those iterated integrals. Just start on the inside, move to the outside. So this is kind of what you might call a roadmap of what we did last time. Now, what we've done just now is we've come up with this idea of a double integral, a 2-index Riemann sum, that makes it easy to take lots of applications and turn them into Riemann sums. A new kind of Riemann sum. So in some sense, this is what we had done as of the start of this page. And now let me explain why this calculation that we just did here is important. This calculation we just did here, we computed volume with a double integral. Let's see how that manifests on this diagram. We computed volume as a double integral. This is the connector between the blue ideas that were kind of seemingly abstract that we were talking about earlier this lecture, and the green ideas, which we kind of already know how to plug and chug through these volume iterated integral computations. So this connects. Ultimately, this is what allows us to connect the dots to get from questions that we're going to want to ask and get to the answers that we need. Did I see a hand somewhere? Yeah.
Has it been proven that the fundamental theorem of calculus applies to 3D?
Oh, no, the fundamental theorem of calculus is just a single variable concept. Okay. Yeah, it's strictly correct. There is no fundamental theorem of calculus for double integrals. Okay. Absolutely not. Okay. You know what? There is something that has some of the earmarks of the fundamental theorem of calculus that does apply to double integrals. It's absolutely not what we're doing here. We will get to that later. But yeah, in the sense that you intended the question, absolutely, there's no fundamental theorem of calculus. I'm just covering my own self there. Relevant to what we're doing here, there is no fundamental theorem for double integrals. So, and that's why, it's a great question. That's why we need this connector. I need to be able to get from this blue world that allows me to connect to applications and relate that to this green world where I know how to compute stuff because they're single variable integrals, and single variable integrals, gosh, you gotta love that fundamental theorem. Right. Okay, so computing a volume with a double integral. This is the critical connection. And in fact, I'm going to rewrite this in just momentarily as, well, look, if double integrals are volume, but volumes are iterated integrals, in fact, that means that double integrals are iterated integrals. And having done that, now I actually don't really, in practice, when we're computing stuff, we don't even really need this anymore. It served its purpose. This volume computation has allowed me to connect double integrals to iterated integrals. We are in business. We're going to answer lots and lots of questions by saying, oh, you want to compute the answer to some physics problem? Write it as a double integral. Recognize that double integral is an iterated integral, and then crank it out with the fundamental theorem. That's our roadmap. This is how we get problems solved in the area of two-dimensional integrals. 3-step process. Everybody with me? Okay. All right. Now, while I'm here, I also want to emphasize some landmines to watch out for. Just like with single variable integrals, I warn you against nonsensical arguments like, oh, well, population, of course, is volume. What? No. Population is people. Right? Population's not volume. That's not a reasonable argument. And again, there are versions of this where you kind of effectively argue that populations are, kind of like a Riemann sum, which of course can be thought of as a volume, and there's unnecessarily awkward arguments like that. But the point is, you don't need to do that at all. Volume is no longer needed in the picture, and furthermore, so if you don't need it, why make an awkward, nonsensical argument to connect to it? That makes no sense at all. So you can't do that. And as we've already seen, right, some pages back, let me hit that real quick here. What we saw here is that if you want to compute mass, for example, you can't just immediately write that as an iterated integral either. Doesn't make any sense. Mass per unit area times length, not a thing, right? So you can't do this either. Right? This idea of I'm just going to immediately write down answers to applications as iterated integrals, there's not an argument there. Right? So we really have to have this three-step process. You need Riemann sums, double integral Riemann sums, to connect to applications. Again, this is not mathematicians being weirdo mathematician, ivory tower, proofy. No, this is a practical, real-world point. Riemann sums are the connection. They're the foot in the door to connecting to applications. You then rewrite them as iterated integrals. You then compute with the fundamental theorem. Okay, so let's see an example here. I've got a certain amount of mass distributed with density given by some expression that depends on location. So different mass per unit area distributed everywhere over a rectangle. And I want to compute the total amount of mass within that entire rectangular sheet. Let me remind you of this notation here. This notation representing this rectangle. Recall that the first part of it there is telling you the range of values of x. And the second part of it here is telling you the range of values of y, right? So, step one is to argue, and I'll go through the step-by-step process in a moment, that mass is a double integral. That's going to be our first first big step. Now, taking that one little piece at a time, the whole is the sum of the parts. If I want the total mass, I can just add up all the little bitty pieces of mass. Next, on any given little piece here, mass is mass per unit area times area. Sure. Right? That's what mass per unit area is for. Right? It's designed to be just that. And then, finally, we say, oh, sweet, check it out. This is literally a Riemann sum. This is literally the definition of this double integral. So, step one, we have this immediate, no funny business argument that mass can be computed with a double integral. That's, let me cleaning up my mess here. That is our first step here, what I like to call phase one of the argument. We've written an application as a double integral. Everybody cool so far? All right, step two is to observe that double integrals are iterated integrals. This part's easy. The double integral I just wrote down, it's this iterated integral. And the bounds are pretty easy to argue. A to b tells you the range of values of x, so x goes from a to b. And likewise, y goes from c to d, so y bounds are c to d. Everybody good? And then, so that's what I call phase two of the argument. And then phase three is the plug and chug part. Crank out the iterated integral by just computing. Just like we did last time. This inside integral is literally a single variable integral. We compute it with the fundamental theorem, straight up. Having done so, we now have an integrand for another single variable integral. Again, fundamental theorem, you just straight out compute it. Okay, so three-step process, and we've now got a reasonable argument that allows us to avoid this what do you do? I don't know what mass per unit area times length even is. Nightmare of a impediment to an argument that we saw last time. Right. Okay. All right. Now, just a Math 219 observation. I do. As y'all know, I've said it a million times. I'm sure I'll say it a million more. It's a class about ideas, right? It's not about the answer at the end of the problem. This is not all I care about here. This is marginally interesting, I suppose, right? What I'm interested in really is I want to see the argument. The argument is what matters. So I need to see, in this course, I need to see all three of these steps, right? So you've got to, again, cleaning up the mess. I need to see that double integral. And then I need to see the iterated integral as well. Okay. So don't sort of, skip over critical parts of the argument. If I can get this thing to erase. Okay. A lot of students will say, oh, mass is this double integral. They just hit straight down to there. That argument doesn't really hold water. Right, you've got to say first that mass is a double integral, and then secondly, you can argue that double integral is the iterated integral. Yeah.
Figured out that.
Okay. Yeah. Cool. Okay. So you gotta give me the whole argument. Now here's a notational shorthand that I hope you'll like. I certainly do. It's extremely common. You eventually notice when you write down enough Riemann sums that when you have a Riemann sum, this is just going to turn into that eventually, and this is going to just turn into that eventually. So how about let's just kind of just as a shorthand to save pencil lead, right? How about we just use those shorthands along the way? And so instead of writing limit summation delta m, we'll abbreviate that with a double integral symbol, and we'll abbreviate that as the d that it's going to eventually turn into. It's just a sort of a shorthand. Don't overthink it. There is no m axis involved in the picture. Don't look for it. It's not there. Right? It's just a notational convenience. So in practice, you can write that instead. And in fact, in practice, once we've done enough of these, which we certainly will have very soon, it's okay to just, m is double integral of density dA. That's totally fine. I just stretched it out here just to make sure that everybody's clear on how that argument works. But this is, totally fine way to write that argument. Is everybody on board? Okay. Now, some more examples of this, what I'm going to call double integral shorthand for developing a Riemann sum. This is just an example. Let's suppose that we have a wall that we're going to be building. And I came up with this example, if I remember correctly, when my house was being built, and they were building a nice sort of stone facade on a certain part of the house. And I was looking at all the stones sitting on the ground, and I was like, somebody's going to have to pick up each one of those stones and lift it up to the height. My gosh, that looks heavy. How much work is it going to take them to lift all those stones on the ground up to where they're going to be on the wall? This is an example of how to compute that. And so here's how I break it down. A lot of details, of course. You notice that this is a 10-foot wide wall, and it's 6 feet tall, and we're setting the origin to be the bottom left corner of the wall, blah, blah, blah. Okay. So, I'm going to take this large job and break it up into little pieces. That's all this, what I have circled in purple there. That's all this says. That the total amount of work is the sum of the amounts of work contained in each little micro task. The micro task being, for example, there's a stone down here that's going to have to get lifted up and put into that position on the wall right there. At some point, somebody's going to have to do that task. right? So how much work does it take to lift that stone? Well, work is equal to force times distance. Not hard to persuade yourself that the distance it has to be lifted is y. That's the coordinate that we're using to represent the height of that location. And now how much force is being applied? Well, the force depends on how much does that little stone weigh. And how much that stone weighs, well, that's going to be, pounds per unit area times area. So we're assuming that we know these stones, it weighs a certain amount of pounds per each little bit of area of stone, how much area of the wall that stone is going to fill. If you're covering more area of the wall, you're going to have more weight in that stone because it's a bigger stone. Okay. So ultimately, you notice we get down to a double integral. But it's kind of nice shorthand to not have to use the bulkier Riemann sum notation and just kind of use these differentials to help you keep track of what the connections are in the argument. Does that make sense to everybody? And the rest of the way through the problem is all kind of hopefully familiar stuff. Double integral is an iterated integral. Density was given. And you can then start computing. There's a single variable inside integral. Don't forget that for the purposes of that inside integral, we treat x as a constant. So that x right there is a constant, and integrate accordingly with respect to y. Right? And then once you've done that inside integral, then you end up with an outside x integral that is literally single variable calculus. Okay. All right. Everybody happy? All right. Okay. Everything we've done so far, we've had rectangular domains. I've got here a rectangular wall, for example. Here I'm computing the mass of a rectangular, sheet of metal or what have you. Here I was computing the volume under a graph of a rectangular, or sitting over a rectangular base. So it's all been rectangular domains. Very convenient when you have rectangular domains. We're now going to set aside that convenience and ask, what if, for example, I want to compute the volume under a graph not over a rectangle, but over some wacky shape like this? Everybody see the issue that we're going to take on here? And here's some really great news. It's basically the same calculation. I'm going to take an iterated integrals point of view on this because it's a little bit easier to see. But imagine that this is your loaf of bread, right? Just like we did when we were doing volume under a graph the very first time. It's still going to be an integral of cross-sectional areas. Those cross-sectional areas themselves are still integrals in the other direction, right? So the green integral, you might say, the dy integral, the outside integral, is in the y direction, and the computing the cross-sectional area integral is in the x direction. That's exactly like before. What in fact is different here? Rhetorical question. And it's just one little thing. It's a little micro thing. It's hardly anything at all. The one little difference is that when I look at this integral that goes from there to there to compute that cross-sectional area, my lower bound is a point right there, which, if you think about it, has a x coordinate there, and that depends on y. And if you think about it, look at that value of y. If you picked a different value of y, you would get a different cross-section of your domain, which would have a different purple point. So we just have to recognize that our let's see how to do this. Our lower bound, for example, for our inside integral is a function. It's a function of that outside variable. Everybody buy it? No big deal. A ditto the upper bound, of course, likewise. Okay. All right. So, next observation I'm going to make is, if I were going to try to figure out, for example, what is this lower bound? How do I know what that lower bound is? Well, I'm going to be looking at this curve right here. Every one of my x lower bounds is going to come from some point on that one curve, and that curve is entirely in the xy plane. I don't need to know about height to figure that out, right? Exactly what this f function is and how tall, blah, who cares? That's got nothing to do with where does the integral start, right? So you only need, the big takeaway is, you only need to understand the domain itself to find your inside bounds. Just the domain. And the tremendous value there is I don't have to draw these really hard three-dimensional pictures. They're hard to draw, right? I don't need to. I can now just look just at the domain itself. Two-dimensional. Much easier art. And this alone is all I need to be able to find my inside bounds. And so, for example, same scenarios before, given a value of y, well, that's going to determine a point on a certain curve. That point will have an x-coordinate that depends on that y. And I can see everything that I need to do the algebra here to get what my bounds are on this merely two-dimensional picture. Okay. So the big picture strategy of how we're going to do this in practice is we're going to identify, for any given value of y, we're going to say, okay, what's the point where my x integral starts? My x integral is going to start at that purple point right there. That purple point will be on a certain curve. That curve will have some equation, and in that equation, I can just solve for x. And I emphasize it's x that I'm going to be solving for. Here, let me make this a different color. I'm going to be solving for that as an x in the equation because it is literally an x coordinate. How we doing? Everybody okay? Let's see one in practice and see it in action, and you'll get the idea. Okay, so I'm going to compute this double integral. Now, before I get into all these details, let me remind you of the big picture strategy of what are we doing here? What's our roadmap? Here we go. This is our roadmap, and you'll notice I've started us here. I've started with a double integral. So let's not worry about what application am I computing. Where did this double integral come from? It came from somewhere. Who cares? We're going to encounter double integrals, and I just want to focus just right now just on this process of turning a double integral into an iterated integral. And so where the application, what the application is that gave this double integral, what's our integrand, what are we computing? Don't worry about it. I just want to focus just on phase 2, just the purple part of the problem here for now. Okay, so double integral. How am I going to write this as an iterated integral? All right, well, we have a triangle with certain vertices. So here's our domain. All right, well, x, what's the range of values for x? X is going to go from 0 to 1. You can kind of see that straight from the picture. Oh, by the way, another really big point. Make sure you always draw yourself a decent picture. A lot of what we're going to write down in the process of writing down these iterated integrals is stuff that you're going to infer from the picture. So really, really important to have a decent picture. And again, 2 reasons why. On the one hand, it's a big help For your geometric interpretation to be able to, make sense out of what you ought to be doing, the picture will be very helpful to you. But the second reason that the picture is important is, again, I emphasize, you have to communicate your reasoning to the grader. And pictures really help to communicate why you wrote down what you wrote down as an even if you can do it in your head, we need to get into your head, right, to see what your reasoning was, and the picture is a great way for you to communicate what your thought process was. Okay, so x goes from 0 to 1, yeah? All right. So next question. We're going to fix a value of x. As we do, we're going to look at this x slice, you might call it. And now let's ask the question, for that x slice, what is this starting value of y? What is the first value of y? Okay, well, I'm going to go through the process like I did above, which is to say that point, well, it's on this curve. That curve has this equation. And let's see, what am I doing here in the first? I'm trying to find what now? Let's see, I'm trying to find my y lower bound. So because I'm trying to find a y bound in this equation, I need to solve for y. Good news, it was already solved for. That was nice. Sometimes you get lucky, and the thing you need to solve for is already solved for. Life is good, right? So 0 is what y is there. And so that's why this lower bound is y equals 0. Everybody good? All right, let's try that process again. This time for the upper bound, again, for a given value of x fixed, on that x slice. Let's see, I'll do this in orange. Here's the last part of that slice, the last part of that x slice. That point that defines my upper bound is always on this curve. Different curve. Thank you, picture, by the way. I mean, without the picture, how would you argue which curve your upper bound comes from? It's not clear. Without a picture, got to have a picture. Your argument's clear if you have the picture to justify the algebra that it leads to. So that point's on this curve. This curve has this equation. Different curve, different equation. Now again, you want to slow down, don't move too fast here, don't forget what it is we're trying to find. We're trying to find here a value of y. I'm looking for my upper bound for y. So in this equation here, I need to solve for y as a function of x. And conveniently, y is an easy function of x. It's just x. Everybody happy? Okay. All right. Cool. And that's all downhill from here. Once you've got your iterated integral, then, fundamental theorem inside out. We've done those before. Okay. Now let's do the same example. Slicing the other direction. Just 'cause. Let's see here. So we've got y now going from 0 to 1. And as we slice perpendicular to the y-axis, as y goes from 0 to 1, we get these cross sections of our area that look all kind of like this. Right? So y goes from 0 to 1. Notice y on the outside now. Okay. Now we fix a value of y. So y is going to be fixed. We now want to focus on, for that one value of y, what is x doing? Well, my starting point for my x bounds is going to be on that point. What do I know about that point? It's on that curve, which has that equation. Now here's where a lot of students will get it wrong. A lot of students will look at that and say, I've seen that one before. Y equals x. Yeah, so we did that one last time, and that gave us a bound of x. So I guess the answer is x. But no, the answer here is not x. The lower bound is not x. Because we're looking for x as a function of y, I need to solve for x in that equation. I need to know what function of y tells me x. And the function of y that tells me x is y, not x. X is wildly wrong. Does that make sense to everybody? Okay. Cool. Whoops. Okay, back to... Okay, so again, for that same fixed value of y, let's ask the next question. Where does x end? What's the last value for my x integral? Well, it's at that point. That point is on this curve. That curve has that equation. Thank you, picture. Gotta love the picture. I don't know how to do this without the picture, frankly. Okay, so in that equation, reminder, I need to solve for x because I'm looking for x bounds. Again, sometimes it's super easy. We solve for x, and that upper bound then is 1. Now I'm being unnecessarily, careful in this example, just because the point is not to get the right answer in this example. The point is to see the process. Points identify curves which have equations in which you solve for a specifically critically chosen variable. Okay. All right. Okie dokie. More examples. Here's another one. We're going to do this one a little bit more quickly. We have a region that is bounded by, let's see here, we've got this curve, y equals x squared, and we've got this curve, y equals 4. So before I get into the calculation here, I do want to be careful with the language. Notice it says D is the region that is bounded by. Let's talk about what bounded by means. This is a loaded term. This means two things. For the one thing, it says that D is in fact bounded. D does not stretch out to infinity in any direction. D is a region that you can put in a box. And these curves, dividing up space into separate regions, only one of those regions is actually bounded. If I were to say, hey, let's look at this region over here, right? Nope, that extends infinitely off to the upper right. That is not a bounded region. It is not bounded by anything because it is not bounded. Everybody with me? Okay, the only region that is actually bounded by these curves is this region in here. So, two things. It is bounded, and also the boundary consists, as it is supposed to, only these curves. Everybody on board? You got to watch out for that language. One of your jobs when you're solving a question of this form is to correctly interpret from the statement of the question what the region is over which you're supposed to be computing a double integral. Okay. All right. So that's it. Let me clean up my picture here. Okay. So actually, let's just clean the whole thing. So let's first, just to get the ball rolling, let's first slice in the x direction. X goes from, I'm going to say pretty clearly from -2 to 2, but let's be careful with that. How do I know that x goes from -2 to 2? Well, my x slices that look like this, the first one is right there, which is where these two curves intersect, which therefore is where x squared is equal to 4. And clearly this lower bound that I'm looking for is negative. It's a negative number for which x squared is equal to 4. -2 is the only answer there. Does everybody see how I did that? Questions? Okay. The upper bound, very similar calculation. The upper bound, the last x slice, well, it happens at that point. Again, it's where these two curves intersect, so it's same algebra, really. I need where x squared is equal to 4, but this time, again, thank you, picture, I can see I need to have a positive value of x. So x equals positive 2. So the bounds, the x bounds, -2 to 2. Everybody believe it? All right. Moving along. Now we fix a value of x. And now I ask for that value of x. Y is going to go from, sort of there to there. So what can I say about this point that represents our starting value of y? That point, well, it's on this curve. Thank you, picture. I need the picture to see that, right? The starting value of y is the point on that curve. That curve has this equation. Wait a second. Reminder, what am I solving for here? I am solving for y because I'm trying to find a bound for y. And solving for y in this equation, I need y as a function of x. Nice. No problem. Already solved for. Gotta love it. And then, likewise, now let's look for the ending value of y. The ending value of y is going to be that point, which is on that curve, which has that equation. Again, reminder, I'm solving for y in this equation. Again, very convenient, just 4. I'm moving more quickly now because we've done several of these. Is everybody still on board? Okay, now again, same question. Slicing the other way. We're going to do our y slicing. Y slicing on the outside. Well, y goes from, well, let's say it this way. This is what our y slices look like. Our first y slice is, come on, eraser. Our first y slice is where y is equal to 0. Our last y slice is where y is equal to 4. Sometimes it's just very immediately clear from the picture. Now we fix a value of y. And having fixed a value of y, we now want to know the range of values for x. Okay, well, that x slice is going to go across like that. Okay, where does x start? Well, it starts at that point. That point is on this curve. Here's another landmine. Here's where a lot of students, again, will screw up. A lot of students say, oh, it's on the parabola. The parabola is x squared. And so a lot of students will incorrectly put x squared right there. Everybody see why that? I mean, you can kind of see the temptation, right? Okay, not following the process. The process, very strictly, that point, yes, it is on this curve. That curve does have this equation. That equation is not x squared. It's not. That equation is y equals x squared. The devil is in the details. Y equals x squared. I have to then remind myself I'm trying to solve for x. I need to find x as a function of y. I need to solve in this equation, therefore, for that x. And x as a function of y involves taking a square root. And I've got to think to myself, well, wait a minute, which one of the square roots is it? Well, I'm looking at this point here, which clearly has a negative x coordinate, and so this starting value of x is going to be the negative of the two ways that I could solve for x in that equation, and so I get the negative square root of y. Is everybody good? Again, big landmine. A lot of students will totally write x squared for the lower bound, and it doesn't make any sense at all. All right, upper bound. Let's see here. My pictures these pictures always get messy. The upper bound for x is going to come from that point, which is again on the same curve, same equation, still solving for x. I still need to solve for x in this equation here. This time, of course, and again, thank you, picture, I can see that the x coordinate I'm looking for is clearly positive. And so when I solve for x here, I pick the positive square root. Is everybody happy? Okay. Okay. Alrighty. So, two different ways you can do it. Which one is better? They're kind of equally correct, but let's be honest now. Which would you prefer to actually compute? I have strong preference here. All else being equal, I don't like square roots. Right? Nobody really does. And let me point out why this might matter. If you think about how the integration is going to go down, when you compute this inside integral, don't forget what the inside integral represents. The inside integral represents the integrand for the dy integral. So think of this inside integral here as being a great big function of y. And when you actually, crank out the x integration, the result will be a great big function of y. And whatever you have here and here are going to show up in that great big function of y. So when you get around to doing your dy integral on the outside, do you really want to do a dy integral where the integrand has square root of y all over it? Ew, right? Those integrals can be a lot worse. This is not just a minor point. This, depending on what your f is, this iterated integral here could be extremely difficult, if not intractable, to compute. This could be big time bad news. Whereas, by contrast, this one here, no square roots at all. Okay, there's a polynomial. Correction, there is a monomial in there. I mean, that's among the easier functions to have to entertain dealing with, so this is much preferred. That makes sense? So how do you decide, right? I mean, before we get into it at all, what is it about the statement of the question here that will tell you, which one of these should I do, before you've done all the slicing and before you've figured out what those bounds are, just looking at the purple only. How do you decide between dy dx and dx dy? And just think about what's going to be a function of what. If you choose to do it this way, you're going to need to find y as a function of x. Cool. If you do it this way, you're going to need to find x as a function of y. You're going to therefore have to solve for x. That's what's going to make your algebra less desirable. Right? So try to arrange your differentials in such a way that the thing you're going to have to solve for is something that you either don't mind solving for or already have solved for, or, just think selfishly. What's going to make your life easiest? And I don't want to have to solve for x because I don't like the result of solving for x. I like solving for y. It's already done. It doesn't have any square roots in it. Much better. Right? So selfishly, I look at this equation and I think, ooh, I would love to have y on the inside here instead of the x. You buy it? All right. Okay. So there's a moral. Think about what's a function of what more conveniently or more naturally, and let that guide your choice. Here is another example that has a punchline. And this one is a little tedious. It doesn't seem like it ought to be. I mean, after all, we've got a triangle. We've done triangles before, whatever. It seems like it should be no big deal, and it is no big deal. Look how this slices up. No sweat. Let me just real quick hit the highlights. Y goes from 0 to 1, and then for any given value of y, x goes from y to 2 minus y. I encourage you to think that through. Make sure that you can reproduce this conclusion as to where those x1 and x2 came from. Right? Points, keep in mind, are on certain curves that have certain equations. Solve the equations appropriately. But look what happens if I do it the other way. Now, innocently, right? Suppose I do dy dx. Okay, well, it's tempting to say x goes from 0 to 2. But here's the problem. For these values of x between 0 and 1, my y upper bound is going to be a point on that curve. But for these values of x from 1 to 2, it isn't, right? I'm not following that curve all the way up there. For those values of x, it is the upper bound for y is on this totally different curve. And I therefore have to deal with this I get a different formula for the upper bound for y, depending on whether x is between 0 and 1 or whether x is between 1 and 2. Different answers. And therefore I have to break it up into two separate integrals. Now, which of these do you prefer? Well, again, I have a pretty strong preference, right? Would I rather compute one integral or would I rather compute two integrals? It's a pretty easy choice, right? All else being equal, we'd much rather do that one. So now again, how do we see that in advance? With all else being equal, we'd like to avoid having to write down all of this stuff only to decide, I don't want to do that after all. Right? So how do we see it coming? And here's my point of view on this. Think about what you're slicing through as you slice. So as I slice in the y direction, my slices look like this. I'm going to say everything's fine there, and let me, just for the purposes of contrast, now let's look as I do my x slicing on the outside. What do my slices look like? They look like this. And the bad news, the bad thing that happened that you can see in this slicing process is that I sliced through a corner. It is because of the fact that I'm slicing through a corner here. That's where my upper bound point moved from the one line to the other line. That's why we have that bad news. It's because I sliced through a corner. So the takeaway on this example is try not to slice through a corner if you possibly can. Every time you slice through a corner, you're going to have to stop the integral that you had been working on and start a whole... Whoops. Oh, come on. We're going to have to stop what you had been working on and start a whole new integral, because which curve is your upper bound changed, and it's all different. And who wants to do that? So try not to slice through corners. Notice up here, no corners. Let's see here. In that slicing process, I never sliced through a corner. Oh, to be fair, there were corners at the beginning. No problem. I was going to start a new integral there anyway. No sweat. Oh, there was a corner at the end. I was done anyway. So that's not a problem. In the middle, between y goes from 0 to 1 there, no corner gets sliced through. Okay. Let's see here. Let's see how far we get. Sometimes you have to do a little work to find what your domain. This is just an example. No really new idea here. Real quick, I've been asked to compute the volume between these two surfaces. If you want to compute this volume, you're adding up a bunch of little French fries again, and your French fries look like this. And the volume of that French fry is a height times an area. It's just that now you got to be a little bit careful here that the height is the difference of the two z coordinates. So what you might call z2 minus z1. Yeah. Height times area of the base, though, gives me volume. Is everybody good on that part? So the tricky bit is, notice in the statement of the question, it doesn't say anything about, over what area in the xy plane. It just says between these two surfaces. So you've got to then infer from this, okay, well, yeah, but these French fries, how do these French fries vary? And, well, there's a bunch of French fries that look kind of like that. And you get one for each little piece of this, what I'm going to call shadow, right? The projection of that volume that I'm trying to compute, that projection down into the xy plane. So that projection is what I need to understand. Everybody good so far? All right. Now, how do you understand that projection, this shadow? And by the way, every question is different. So this is not an algorithmic thing, but I'm going to show you what happens in this case, and this is a pretty common scenario. But I argue that this is defined by where its boundary is, and that boundary is the XY projection of that which you might call edge, or I guess edge is anyway, it's where those two surfaces intersect. Is that cool? So, a lot of students, noticing this geometrically, will say, okay, all right, so I need to find the intersection of these two surfaces, and another landmine. A lot of students will mess this up. A lot of students will say, I'm going to set these two equations equal to each other. Again, you can see the temptation. You want to know where they intersect, and there's this temptation to say, well, then I want to set equations equal to each other. I think if you take a moment and think about it, that's not a thing, right? Dumb example, and I emphasize the dumb here, but just for dramatic purposes, what would happen if I needed for these two equations both to be true at the same time? Would I set 3 equal to 6? No. Right? This is not a thing. There is no such thing as setting equations equal to each other. So, and yet I have seen a large number of students over the years write down this kind of nonsense. So again, make sure not to step on that landmine. What we do here is we are looking for, let's see, do I have a picture? No. I am looking for points down here. I'm looking for X's and Y's where the distance up to the paraboloid, which you might call Z1, and the distance up to the plane that you might call Z2, I want those two distances, those two heights, to be equal. Said differently in the algebra, what I really need is for this Z to equal to this Z. Everybody see how that's very different, right? So that's what you need to do in these kinds of questions. And let's see, I'll get this on the page here. Yeah, so the first Z is x squared plus y squared. That was easy. It's right there looking at us, and you gotta like it when that happens. But this other Z is not something that we were just straight already looking at. I had to do a little bit of algebra to solve for that Z. And then, algebra ensues, and there's your domain. And I'm going to point out, don't forget, I've already made this pitch, but it's really important to be able to complete the square. That's one of the critical bits of algebra here. So make sure you remember how to do completing the square, and I know that gets kind of glossed over in a lot of high school algebra classes these days, but make sure you can do that. Okay, and likewise over here, of course. Okay, I'm going to make a quick wave of the hands at section 5.3. It's by far the shortest section in the book in terms of ideas covered. There's actually very little in here to say. The innocent observation is that sometimes when you write down an iterated integral, there's just not that, there's just nowhere you can go with it computationally. So for example, you look at this inside integral here. I need to compute an integral of e to the x squared dx. And you can't. There's no way to do that integral, as it were, without, writing down power series and stuff like that. So there's no closed form antiderivative for e to the x squared. So this is bad news. This integral is rough. All you have to do here, at least in this case, and the strategy that they're describing in section 5.3, is to just reverse engineer what the picture is of the domain that led to this integral. And so now y'all know how to take a region now and turn that into an iterated integral. We're just going to go backwards, take the integral and reverse engineer what the region is. And you can see what's going on here is that y goes from 0 to 1. Cool. There's y equals 0. There's y equals 1. The lower bound for x is where x is equal to y. The upper bound for x is where x is equal to 1. So all I did there is just undo the usual process of slicing up a region. I just kind of worked backwards. And once you understand what your region is, and you can see it right here in the picture now, a region is this triangle right here. Okay, well now we're just going to slice the other direction. So forget about all of what we did before. Forget about this the original integral that led to this. Slicing with the differentials in the opposite order. And y'all can see these details on your own. You have x going from 0 to 1, and then y is going to go from, well, there to there, but that's going to give these bounds. And it turns out this integral is a lot more doable. For one thing, this is a dy integral on the inside. X is a constant. That means e to the x squared is just a great big scary looking constant, but it remains its constant. So super easy to take an integral of. And that leads to this integral. Let's see here, let me just erase all this. This integral here, not the same integral. You do see the scary e to the x squared here, but because of the inside integral and how that worked out, there's this very helpful extra factor of x, and you can totally do this integral with a substitution. So this is what they call reversing the order of integration, and it's not that deep of an idea. Again, it's just a matter of reverse engineering to find what your domain is, and then just slice in the other direction. Okay. And we're out of time, so calling it a day right here, and we will pick up here next time, and I hope that we will start catching up soon. I know we're behind schedule. We'll make it. Everything's fine.